linear algebra. I hope you're not surprised of seeing me on this side of the screen. Here we go. Here in this video, we want to show that 1xx squared is a basis for P2. And from there, we're going to deduce what's the dimension of P2. We can answer immediately, of course, but we first want to prove that 1xx squared is a basis for P2. And what tools do we need? Okay, so the tool that we need is here. So if B1, BK is a basis, or actually this is the definition of a basis, right? B1 to BK is a basis if the set is linearly independent and the span is equal to the vector space. In this case, it will be P2. Okay? And the proof is based on, well, actually, no. It's not that the proof is based on this theorem, it's that there's a very strong connection between the proof of this and this theorem. They both follow the same technique. Okay, so that given n plus 1 with distinct x coordinate, there's a single polynomial of degree at most n passing through these points. So if we can prove that this is a basis, then from the unique representation theorem, any polynomial of degree 2 can be written in a unique way into like as a linear combination of our basis elements. So that's where this theorem comes from, or that's the connection there is between this theorem and the fact that we're going to find out that this is a basis. Let's begin. Okay. So again, like a little pre-setup is to write what does it mean for P to be an element of P2. It means that we can write it like this. We are sure that it doesn't have a term of degree 3 and higher. And we're also going to set up labels because it will help us with the proof. We're going to call B1 to be 1, B2 to be x, B3 to be x squared. Now be careful because we're trying to prove that this is a basis. We don't know it quite yet. So we cannot assume it. So be careful whenever you use this notation. With that in mind, let's get started. So the first thing we will do is we will prove linear independence. And for that, we need to recap a little bit the definition of linear independence. So B1x, B2x, and B3x, okay, is Li if, so in other words, if C1 B1x plus C2 B2x plus C3 B3x equals 0, okay, well, 0 in this case, remember the context, it is the 0 polynomial, right? So I'm going to write here like O of x, that is like 0, of course. Mean that C1, C2, C3 must be all 0. So implies C1 equals 0, C2 equals 0, and C3 equals 0. And the idea is actually quite simple. We're going to evaluate both sides at 3 different values of x, hence the connection with this theorem. So we're going to say here, okay, let's have... So this is a polynomial. Let's evaluate C1 B1 of 1 plus C2 B2 of 1 plus C3 B3 of 1. Well, this has to be equal the 0 polynomial of 1. Okay, so from there, now we evaluate each of them. We're going to get C1 times 1 plus C2 times 1 plus C3 times 1 is equal to 0. Okay, so let's actually just color code here. And then we're doing the same for 2 other values of x, and we'll pick very easy values. So we're going to pick 0, for example. So C2 B2 of 0 plus C3 B3 of 0. That's equal to 0 polynomial when x is equal to 0. So again, here, I'm just going to write the canvas. So we're going to have here, be careful, B1 of 0 is going to be equal to 1. But the other 2 are going to be 0. And here we're going to get 0. Then finally, we do it at -1. Okay, so the idea is really to get some nice values. Okay, so B3 of -1. That has to be equal to 0 polynomial at -1, which means, again, so C1, C2, C3 is equal to 0. So here, what do we have? B of -1 is obviously 1, but there we will have a -1, and here the -1 squared. Let's actually write -1 squared so that you see what's going on. But yeah, like this will be a system that we will now solve. Okay, so I can erase all of this. Okay, let's actually just erase that part. Okay, so now we have this matrix, okay, that we're just gonna fill in the numbers. What could we do to simplify our work? Well, actually, okay, let's just copy paste them as they are. I don't really care that much. We're just gonna do like row operations when suitable. Okay, and then here we have 1, -1, and then 1 with 0. Okay. So, okay, so I think we could go ahead. Okay, let's actually just row reduce this like from beginning to end. So row 2 becomes row 2 minus row 1. Row 3 becomes row 3 minus row 1. So what are we going to get? So 1, 1, 1 slash 0. Then we're going to have 0, -1, -1, 0. And finally, we have 0, -2. And then row 3 minus row 1 is 0. Perfect. So we need one last row operation. That is row 3 becomes row 3 minus 2, row 2. So what we're going to get here is 1, 1, 1 slash 0. Then 0, -1, -1, 0. And finally, 0, 0. And then this is going to give us +2. And as you can see, you have a pivot in every column, which means that the system has a unique solution. And knowing that the system is homogeneous, we know that this unique solution is the trivial solution. Okay, so I won't write exactly what I said in words, but that's it. Like as we can see, this system has a unique solution. So C1 equals 0, C2 equals 0, C3 equals 0, which means that we're good. Number 1 is verified. So 1 is verified. Okay. By the way, this was the hardest part of the proof. Okay. Now that we have number 1, number 2 is actually quite easy. We want to verify that the span of these 3 elements is going to be the entire set P2, right? So let's write again what I wrote at the beginning. I think what I wrote is that P is in P2, okay? If I will say here if and only if, actually, because this will help in our reasoning. I know it's a definition, but let's put the if and only if. So P of x is equal to A1, A0 actually, plus A1x plus A2x squared. Okay, for some A1, A0, A1, A2 being real numbers. Okay, now I'm going to sneak in the basis elements. Okay, so I'm going to write here, if and only if P of x is equal to A0 And then I'm gonna write like b1 of x, which is just equal to 1, right? Plus a1 b2 of x, which, as you can see, is just equal to x, and plus a2 b3 of x, which is the one that's equal to x squared. Okay, I need to erase this. We don't need it anymore anyways. So what can we conclude from there? Okay, so P is in P2 if and only if P is a linear combination of B1, B2, B3, right? B1x, B2x, B3x, okay? So this means that P is in P2. Let's now write it. This is the important part. P is in P2 if and only if P is in the span of these three vectors, right? So, well, let's name them again. B1, B2, B3. So, of course, this is what it means for the two sets to be equal. So from there, we get that P2 is equal the span of B1, B2, B3. And let's actually remove the x, right? B1, B2, B3, which I should have done here as well, by the way. But it's not that important. Meaning that property number 2 is verified. So as a conclusion, since 1 and 2 are both verified, 1x x squared is a basis for P2. Okay? So this was the biggest part of the problem, okay? Was just proving that this is a basis. Now let's answer this small question. Now that we know that this is a basis, what is the dimension of P2? Well, remember that the dimension of a vector space is the number of its basis element. So because we have 3 basis elements, the dimension, so actually, let's write it over here. The dimension will be equal to 3. So number of basis elements, which means that the dimension is 3. All right, hopefully this helped. See you either in class or in the next video.